The following questions will revolve around the extraction of sugar beet. To get you a heads up on how to derive the mass balances for such a system, we're going to derive the mass balances for question 3a. If we look at the extraction, we see that we have two inlet streams, one containing the beets that contain the sugar, and one containing a water stream to which we will extract the sugar. The system will also contain two outlet streams. The first stream is the water stream. This stream contains the extracted sugar. The flow is slightly corrected for the amount of water that leaves the system with the leftover beets. The second outlet stream is the leftover beets that still contain a fraction of sugar, x1. So let's first define a problem. What is asked from us? It is asked from us to derive the fraction of sugar extracted to the water phase. Moreover, it is asked to calculate the tons per year of sugar extracted to the water phase. So how can we define this problem? In the end, the extracted amount of sugar that is extracted to the water is equal to that amount of sugar that enters the system with the beets minus the amount of sugar that is still left in the leftover beets. To describe this mathematically, this should be equal to b0 minus bx1. As b and x0 are already known values, it singles down to determining x1. So let's derive the mass balances to determine x1. When setting up the mass balances, we see that our inlet streams will have to be equal to our outlet streams. Therefore, we can set up the mass balances like this, where the inlet streams multiplied by their respective sugar fractions are equal to the outlet streams multiplied by their respective sugar fractions. The first thing we can do is split out this part of the equation to simplify it a bit. When we split it out, we can see that these two terms cancel each other out. Moreover, we can make two assumptions. First of all, we can assume that our water extract stream that enters the system contains no sugar, setting the I0 fraction to 0. Moreover, based on the partition coefficient, we can calculate a value for y1 based on the fraction of x1. When implementing these in our mass balances, the mass balance simplifies to the following expression. We see that this expression is no longer dependent on any fraction within the extract stream, within the water. Now, let's divide this equation by bx0, because when we do that, we see that we get the following expression. This expression we can simplify again a bit by separating out x1 over x0. When separating out x1 over x0, the following part of the equation arises that you might recognize. This is equal to the separation factor, because you might recall that the separation factor is equal to the partition coefficient multiplied by the extract stream divided by the stream from which the compound has to be extracted. Now let's insert the separation factor. If we insert the separation factor, we obtain the following expression. We can rewrite this expression to yield an expression for x1. This expression depends only on x0 and the separation factor. As all the values in the separation factor and x0 is known, this means that you can now calculate x1. Using this equation, you will be able to derive the final answer to the problem. Moreover, the system on how we set up mass balances can be very useful for the following questions.